So, in the last lecture we are looking at the abrupt changes in climate in the North Atlantic as we came out of the last ice age. And the key factor there was that the warm salty water coming from the tropics. This water is warm because it is on the surface coming from the tropics, which is at high temperature. It is salty because it is losing water by evaporation, but not salt. So, this warm salty water is heavier than the layers below it, which are cold and less salty, and so this water starts sinking, okay, around Greenland in many ways. Okay. And when it goes down, it forms what is called the North Atlantic deep water. Okay. So, this water, which is warm and salty, cools as it approaches Greenland, and because it cools, it becomes even heavier and it drops down, and at two different layers. One is called upper, one is called lower, depending on its density. Then it flows southward towards the southern hemisphere. And this pattern of change in circulation between Greenland and Antarctica is what is called the Atlantic Meridional Ocean Circulation, AMOC. Okay. So, this changes in AMOC had a big impact on the climate of Greenland, okay, and you will see ultimately had impact on global climate. So, this is what we talked about in last lecture, and we will continue in this lecture, and I mostly talk about AMOC, but note that AMOC and NAW are connected. They are a part of the same system. So, in some of the graphs I showed you, instead of AMOC, they would have shown NADW, North Atlantic deep water. If AMOC accelerates, you have more formation of NADW and vice versa. So, remember that the two words are sort of used interchangeably, although AMOC refers to the large scale meridional ocean circulation between south and the northern hemisphere. Well, NADW, the North Atlantic deep water, refers to the formation of this water around Greenland, because this warm salty water, this water after cooling goes down and settles down at a lower level. Now, to give you a clear picture, I am giving you the vertical cross section, okay, where you see the warm salty water near Greenland cools both by cooling to the atmosphere as well as because ice melts here, and that water, after becoming cooler and heavier, settles down at the interior of the ocean in the Atlantic. Now, at what level this settles down depends on the density of this water. Some water may settle down here, another may settle down here. Okay. So, the precise layer where this water, which is coming down because of higher density, where it settles depends on its density. Okay. In the meantime, in the Antarctic, the water in the Antarctic is much colder, and it comes all the way down and settles at the bottom. It is called the Atlantic bottom water. Okay. So, these names are given by oceanographers because once you are away from the top layer where there is mixing due to winds, below that there is hardly any mixing. Okay. Once you get below the upper mixed layer of the ocean, the water maintains its identity. The identity of water is defined by its temperature and salinity. There are only two parameters. Temperature salinity tells you what is the characteristic of that water, and as that water goes down into deep ocean, you can clearly identify it as to where it came from, because of its temperature and salinity is unchanging. It changed when you are on the surface here because of evaporation and other factors on ice coming in. Once it goes inside the ocean, below the mixed layer, the blobs of water maintain their identity, and so they are defined by, if a certain temperature salinity is called NaDW, if it is a different salinity and temperature, we know where it came from, we call it Antarctic bottom water. And there is Antarctic intermediate water. This water has a slightly lower density, so when it comes down it settles somewhere here. Okay. So remember that the density depends on salinity and temperature. So if the temperature is low, then it will settle deep down. If the temperature is high, it will settle a little higher. If the salinity is low, it will be at a higher level. If the salinity is high, it will dip down. Notice the salinity change is not going to be that easy unless there is some fresh water coming in, like ice melting. So the main change that occurs is the temperature, if it loses heat or gains heat. Okay. So remember, these terms are used because they identify that water for long periods, for centuries together, that water maintains its identity. Now we are going to talk about, we talked about one event in the period between 20,000 years ago and today, but now in order to fully understand how this phenomena occurs, I am comparing a paper which compared two of these events. One was what I already studied, in which the North Atlantic region near Greenland went through a cold period called Younger Dryas and then immediately became warm. The same thing happened 100,000 ago earlier. Okay? And this data is from ice core. Okay? Ice core data is very well documented, and we have data going back to 600,000 years. Okay? And in every one of those data sets we see these kinds of events. That is why they are called DO events, when there are oscillations of the ocean system. And so since there are many of them, it is good to compare them and see whether your models are actually able to simulate these changes. Okay? We saw one of them that happened in the last 20,000 years. Now we will compare them with something happened 100,000 years earlier. So what this paper, which talks about this work, published in Scientific Reports in November 2011, is that there were significant differences between these last two deglaciations in the Atlantic. Okay? So they present the transient simulations from a model which is coupled ocean atmospheric general circulation model, and they are focusing on the changes in the last two deglaciations and the impact of ice sheet melting and discharge on climate changes associated with the AMOC. Okay? So they show that these events occurred due to gradual changes in the ice sheet melting discharge, and of course changes in carbon dioxide, methane, which is radiative forcing. So they say that in the previous deglaciation, not the one in the last 20,000 years, was simulated when the ice sheet discharge was greater than in the last deglaciation by a factor of 1.5. Okay? So what they say is that the orbital condition, that is the Earth's orbit around the Sun, was not same 20,000 years ago as compared to 120,000 years ago. Okay? So, in this 100,000 years, there is a big change in the Earth's orbit around the Sun, about which we will talk much more in the next lecture. So, because of that, these two deglaciation occurred in a different manner. Okay. And the simulation they use was similar to what we discussed with trace model, around 280 kilometers latitude longitude, and ocean being somewhat finer resolution. Okay. Now, here is a comparison, and you see there are three curves here. Okay. And all of them talk about the latitudinal variation of the heat transport, how much heat is transported, okay, in petawatts, that is 10 to the power 15 watts. Okay. And the red is the simulation for the deglaciation which occurred 130,000 years ago, okay, long time back. And we see that the heat transport was somewhat less than the black line, which represents what happened around 13,000 years ago, okay, which we discussed in the last lecture. So, the amount of heat transported is a factor of, I would say, almost 3 higher here. And they attribute this to the fact that the orbit of Earth around the Sun 13,000 years ago was quite different from that 130 years ago, and that changed the amount of radiation falling in the northern hemisphere during summer. Okay. So, that is what controls this change. Now, here is a comparison for the temperature change in the atmosphere between the period 15 to 13,000 years ago compared to 133 and 131,000 years ago, and the temperature scale is given here. And you see clearly the warming was much more during this event, okay, a warming event, which we call Birling Aneroid, and the warming was around 2 to 3 degrees in Greenland, while 133,000 years ago, when that occurred, the warming was around 1.5 degree. So, there is a big difference between these two. And second big difference I wanted to notice is in the southern hemisphere. In the southern hemisphere, the temperature was colder than normal by around 2 to 3 degrees, while here it was warmer. So, you see a big difference in the north-south temperature variation in the most recent deglaciation compared to what happened 100,000 years ago, and they attribute this to the changes in the Earth's orbit around the Sun. Okay. Here is a picture of what is happening in the southern hemisphere. This is Antarctica in a model, and these lines show the melting of the sea ice. Okay. And what you see that 15,000 to 13,000 years before present, the ocean around Antarctica was around 120 degrees colder than the present, while in this period 133 to 131 years ago, Antarctica was about, I would say, 0.5 to 1 degree warmer. Okay. So, there was a different climate, and so last interglacial, this is not the, this is the present interglacial, this is the last interglacial, actually was warmer than the present day. So, it is very important even to study, because if you want to know what is going to happen to Earth's climate in the next couple hundred years, then it is good to study this period, because it was as warm as or warmer than the present. That is why this period is of great interest. Now, this shows I want you to look at the time axis here. There are two time axes, one going from 21,000 years ago to 9,000 years ago, other one 138,000 to 128,000. So, approximately 10,000 year period in this case and 12,000 in the other case are superimposed. Red line correspond to the last interglacial, that is 130,000 years ago, and the black line correspond to the most recent deglaciation which occurred around 15,000 years ago. Okay. And what you see is that if you look at the deep ocean, interestingly was somewhat colder. Now, they are talking about average between 60 south and 60 north and depth from 500 to 2,500 meters. Okay. That is the subsurface ocean. Well, the deep ocean is defined as anything deeper than 2,500 meters. Okay. Now, let us look at the deep ocean first. What's the deep ocean? You see, deep ocean actually was colder during the last interglacial than the present event which occurred 50,000 years ago. Okay. So, as this warming occurred, that boiling aneroid, can see that the deep ocean was 0.5 degree warmer than what it was in the last interglacial 130,000 years ago. But if you come to the subsurface, which is average between 500 to 2,500, you see that the last interglacial 130,000 years ago was warmer always than the present warming event which occurred 50,000 years ago. And this is combining Pacific and the Indian Ocean. We look at Atlantic only, which is of interest to us. You see, Atlantic also, the last interglacial 130,000 years ago was warmer than the present interglacial 50,000 years ago, and you see that the abrupt warming we saw, the boiling aneroid, was not seen in the last interglacial. Okay. So, these temperature differences had an impact on how this event, the Heinrich and the Younger Dryas and the boiling aneroid, how they behaved in the subsurface of the Atlantic Ocean. Okay. So, by studying two deglaciations separated by 100,000 years, we are able to understand the impact of the deep ocean and the subsurface ocean temperatures on these events. So, these events are sensitive to what was the ocean temperature below the surface, and so by comparing two events we are able to understand the role played by temperature of the ocean. Now, here is a comparison of the AMOC, which is of great interest to us, and again I want you to notice the two time scales. The red is the last interglacial 130,000 years ago, black is the present interglacial starting around here 19,000 years ago. And you notice that there were large changes in AMOC in the last interglacial in the beginning, and then there was no change. While in the present interglacial, which started warming 15,000 years ago and then went through this Younger Dryas event and then came out with boiling aneroid, this occurred at a time when we did not see a similar event 100,000 years ago. So, these are separated in time, and that shows that conditions were somewhat different. So, these warming events occurred about, I would say, few thousand years earlier in the last interglacial compared to the present interglacial, and you see that December to February surface air temperature, okay, is different here compared to here. Okay. So, again they are able, by studying two different warming events separated by 100,000 years, they are able to show how sensitive these are to conditions of the ocean and the atmosphere. Okay. Now, recently a paper was published by Smead et al. 2008. They used actual data. Now, you are talking about what is happening in the last 20 years. They used actual data in an array of instruments that was placed at 26 north in the Atlantic Ocean, and they show that AMOC has been in a state of reduced overturning circulation. AMOC is weakening since 2008 as compared to 2004 to 2008. So, this immediately caused a lot of concern. Is the AMOC beginning to decline in response to the CO2 increase? That was the question. And this change in AMOC state, they are saying, is concurrent with other changes in the North Atlantic, such as the northward shift and broadening of the Gulf Stream and altered patterns of heat content and sea surface temperature, and these changes resemble the response to a declining AMOC predicted by Köppen climate model. So, they looked at the observation after 2008, and they are saying there is a hint that there is a decline in AMOC, which models predict will happen because of the increase in CO2 and global warming. So, this created a lot of concern and excitement. And if you look at now this graph of changes in greenhouse gases at the end of the last ice age, that is about 15,000 years ago, you see a big difference between carbon dioxide and methane. Okay. During Younger Dryas, the cold event, methane dropped substantially from around 600 parts per billion to around 450 watts per billion. Okay. So, it was around 300 parts per billion, and then it slowly warmed up as the declacial event started, and during the Berlin-Elleroyd event it went up to 650, but then suddenly the AMOC declined and the Younger Dryas happened and the methane dropped. This shows that methane is sensitive to the temperature of the ocean, but in the case of carbon dioxide you do not see such a impact. Okay. Carbon dioxide continues to increase in the atmosphere. So, this is an interesting issue which we will discuss in either today's or tomorrow's lecture. That shows that carbon dioxide increasing the atmosphere at a time when human beings were not there, remember this is natural variation, is governed by different phenomena than methane. So, methane changes do respond to warming and other factors, because methane is produced by the melting of the permafrost. Permafrost is there all over the northern part of the Eurasian continent, lot of frozen soil right from Sweden all the way to Siberia. And as the global warming occurs, remember that we have warmed by 1.5 degree global mean since the last that is pre-industrial period 1750, but in the polar regions the warming is more like 3 to 4 degrees. Okay. This is thing we all know, understand. This is due to ice albedo feedback, where as the ice melts in the polar region, more radiation is absorbed and warming accelerates. This does not happen in India. Most of India does not have snow and ice except Himalayas. So, most of India shows less warming than the polar regions. Okay. And that causes, of course, carbon dioxide to increase and methane decrease, but methane and carbon dioxide respond on different time scales. Methane is a gas which has very short residence time, 10 to 20 years at the most. Okay. So, it reacts immediately to some methane being emitted by melting permafrost. So, this change you saw here, sharp change, is a response to cooling. Okay. When the northern hemisphere cooled suddenly, the permafrost would have refrozen. Okay. So, methane emission will stop. CO2 does not respond to that quickly to permafrost. It will, but carbon dioxide has a much longer time scale in the atmosphere. So, you will see changes on a much longer time scale. So, this is a very interesting feature which we will come to later. So, why did methane change but not CO2? The natural concentration of methane in the atmosphere is driven by a range of sources. I talked about permafrost. There is also methane hydrate on the seafloor. There is also biomass burning that occurs naturally. Also wetlands. So, wetlands produce a lot of methane. Okay. So, all these changes occur very quickly because methane has a short residence time. And other thing is methane is oxidized by the OH radical in the atmosphere. So, methane becomes carbon dioxide and water vapor. So, even if the source of methane has not changed, if the OH radical in the atmosphere changes, then it will reduce methane by oxidation. So, methane is a very quick responding gas and shows a lot of rapid fluctuations, and we also observed this in the last 50-40 years, rapid changes in methane, and is not fully understood because there are a lot of natural sources of methane in the atmosphere, and like wetlands, permafrost, biomass burning, forest fire, so many other possible reasons. And so, you will see lots of rapid changes in methane, which you will not see in the case of carbon dioxide. So, let us now summarize what is given in the recent paper by Melverka and Vallée in the Climate of the Past, published last year. There is uncertainty whether current IPCC class models can effectively represent processes that cause DO oscillations, that is Dansgaard-Oeschger oscillations. Okay. They claim that they have shown that the reduced ice sheets relative to last glacial maximum and the low obliquity, that is the inclination of the Earth's orbit, and low to medium CO2 values are more likely to lead to unforced quasi-oscillatory DO type behavior. However, the simulations need to be run long enough to allow strong positive AMOC feedbacks, that is increase in CO2 and methane, along with negative feedbacks on time scales which can then lead to DO type oscillation. So, they are claiming that around 40% of simulation set up with full last glacial maximum like conditions have run less than 2000 model years, which makes it difficult to tell whether any of these simulations are capable of or likely to exhibit DO oscillation. Okay. So, what they are claiming is that these simulations do not reproduce the DO type behavior, and this could be partly on account of the fact that the model simulations are not long enough. Okay. So, they are not sure whether the same model, if run for 10,000 years, will produce some de-oscillations. So, this has been a point they made. So, there will be many more simulations done in the next 10 years to understand this issue. Okay. Now, let me show you what happens when you take a model and suddenly increase carbon dioxide by a factor of 4. Okay. This is done because you want to do a sort of a shock treatment to the climate model to see what happens. So, you take a model which has reached some steady state, LGM conditions, and suddenly increase the CO2 by 4 times. Now, why 4 times? Because that is a big signal. If you do 2 times, sometimes you do not get enough signal. Okay. So, although this may look artificial, it is done to understand how the climate model responds to large changes in carbon dioxide over a very short time scale, abrupt change. Okay. The abrupt change is a very popular way to understand. So, this abrupt change occurred in this model in year 1, okay, and you can see AMOC responds immediately to abrupt change, and AMOC rapidly declines. Okay. They are showing AMOC in the black, the sea ice in red, and the sea surface salinity in red. Okay. So, what you see is as soon as you increase CO2 4 times, the sea surface salinity declines rapidly because of melting of the ice sheets, and naturally once the sea ice melts, the sea surface salinity declines rapidly. Okay. And after many 100 years, slowly the system recovers and does not quite reach, but almost reaches the original value. Okay. So, they talk about a fast reduction in the first 100 years, this one, and a slow recovery, then a fast recovery, and a damped oscillation. So, what you see is that when a system is subject to a shock increase in CO2, there is a very quick response within a couple of 100 years, and there is then a slow recovery and then a fast recovery, and then some kind of steady state oscillation. Okay. Now, this is very illuminating, because although in the real world we are not subjecting the earth to abrupt increase in CO2 by a factor of 4, but we are changing CO2 at a rate which earth has not seen in the last 50 million years. Okay. So, our CO2 has increased by 150 parts per million in around 170 years. Okay. This is a large change. Okay. This kind of change has not been seen in the past in the Earth's history, whatever data we have, the proxy data, over the past 50 million years. So, this is a good way to understand how Earth's climate will respond to a rapid increase in carbon dioxide. Now, let us go back and look at the proxy data for the last 90,000 years. Okay. This is from a ice core. 2 of them are from Antarctic, and 2 of them are from Greenland. Okay. And first thing you must notice that, let us compare the blue and the red and the blue curves here, and you see the Greenland ice core shows a lot more fluctuations than the Antarctic ice core. So, this shows that northern hemisphere being primarily a land dominated hemisphere, there are much more abrupt fluctuations in climate than you see in the southern hemisphere, that is Antarctica, where the ocean dominates. Okay. So, we will stop here and continue this lecture in the next period.